Here we're going to have a look at the Arrhenius equation. I will say from the start that what I'll be mentioning in this video is probably a little bit above and beyond what you'll actually need for the exam, but it will hopefully help you understand what this equation is telling us in a little bit more depth. The equation is one that you don't need to recite. It's one that will be given in the exam, and it is as follows. Now, K is the rate constant. A is something called the Arrhenius constant. Now, the units for the rate constant and the Arrhenius constant are the same, and they vary depending on the order of the reaction. So remember, rate constants, the units there vary according to what the order of the reaction is. Now, EA is my activation energy, and them units are in joules per mole. My R is the gas constant, which was the same gas constant that you looked at in when you looked at the ideal gas equation, and that's 8.31 joules per Kelvin per mole, and that's a value which will always be given to you. And then T is the temperature, and that is always in Kelvin. Now, remember the three things which can affect how fast the reaction occurs. The three things are the collision frequency, how often they collide in per unit time, something we said called the steric factor, they collide in the correct orientation to react, and the fraction of particles with the activation energy, how forcefully they collide. And the beauty of this equation is that all three of those factors are incorporated into the equation. The A value here, this Arrhenius constant, is actually a product of the collision frequency and some steric factor. What I'm going to highlight here now in yellow, this here is, that term there is the fraction of particles with activation energy. Now, if I obviously double my collision frequency, double the number of collisions by, for example, doubling the concentration, we get a double in the rate constant. So certainly if it's a first order reaction, you double the concentration, therefore you double the collision frequency, you double this K value. But what we're going to look at is how temperature affects this K value. Now, if I plot a graph of temperature against the rate constant, what we find is that it's not a proportional increase. It isn't the case if I double T, I double the rate constant. If you were to plot a graph, you'd get one that looked like this. It's what we call an exponential increase. What that tells us is that a small increase in T causes a very large increase in K because of this exponential term. So we can say then the graph is telling us small increases in T cause large increases in K. And we can show that by just putting some numbers into the equation. So let's do a calculation. Now, I'm going to say that A is 1 times 10 to the 10, and we'll give the units there seconds to the -1. My activation energy, we'll say 75 kilojoules per mole. R is obviously 8.31 joules per Kelvin per mole, and we'll say the temperature is 300 Kelvin. Now, if we plug them numbers into the equation to work out K, the first thing we need to remember is we need to convert that kilojoules per mole here into, as the equation tells us it should be in joules per mole. So it's 75,000 divided by 8.31 times 300. And when we do that, we get an answer of 8.60 times 10 to the minus 4. Again, the units for K are the same as the units here for A, so my units there are seconds to the minus 1. That's at 300 Kelvin. If I was going to change the temperature, let's increase this by 10 degrees, a very small increase in T. I'm now going to change this now to 310. So if I change this to 310, everything else is constant, I actually get now a value of 2.27 times 10 to the minus 3 seconds to the minus 1, and that's at 310 Kelvin. So we can see there a 10 degree increase has caused the rate constant to more than double. So that backs up the statement that a small increase in T causes a large increase in K. So we said then that as this T value gets bigger, my rate constant gets bigger. But what happens then if I keep increasing the temperature? This fraction here will become bigger. As this T value gets bigger, this fraction gets bigger. At infinitely high values of T, this fraction will eventually become 1. So at very high T values, this fraction here becomes equal to 1. And again, try that out on your calculator. What that means then is all the collisions at very, very high temperature values, all the collisions are successful. So now that K is going to then be equal to A, and at very high values, then this fraction then is equal to 1. What that tells me then at infinitely high temperatures, all the collisions are successful and K then becomes equal to A. What that tells me then is what A actually is. A is the rate constant if all the collisions are successful. And they will be at infinitely high temperatures. And that's why this Arrhenius constant is so very, very large, because it's what the rate constant would be at infinitely high temperatures. Now, I will stress that a lot of what I've said here will probably not be testing the exam, but what it is doing is giving us a deeper understanding of what the Arrhenius equation is telling us. The key thing to remember really is that this bit here, rate constant varies with temperature, but it's a small increase in T causes the largest increase in rate constants.